Nusselt in 1923 developed analytical solutions for the laminar film condensations, and he could develop an average heat transfer coefficient H of L for a vertical plate with the length of L that we have the laminar film condensate. So this is by Nusselt analysis in 1923. He developed a relationship for the average heat transfer that can happen at this is X and this is Y for this condensate flow for this system, and the correlations is the equation is the ones that you analytically develop. 943 G mu L rho L minus rho V HFG KL to the power of 3 divided by mu L T sat minus TS times L to the power of 1/4. Recall that for the latent heat of vaporizations, what we said was that here the vapor releases the heat and the condensate is cooled down from like T sat to TS here at the solid surface. So instead of HFG, we are using a modified latent heat, which is HFG plus 0.6 S specific heat to the liquid T sat minus TS. So we replace that one here and put H prime FG in the Nusselt equations. And this is for the Reynolds number. This is for the laminar. So the conditions here is the Reynolds delta is going to be less than 30. Now this one was developed for a vertical flat plate, but the same equation can be used with the confident. It can be used for inclined plates, inclined flat plates. The only thing here is, like, let's say if we have these inclined plates and this is the angle theta, then we would replace G with G cosine of theta. Of course, this is valid for the range of theta. Small theta, generally theta should be less than 60, or it's not valid for large theta. Definitely for theta 90 is not really valid. This is for the inclined plate. It also can be used for condensate over a vertical tubes, okay? Condensate for the inner and outer surfaces of a vertical tube with the conditions that the radius of the tube or diameter of tube is much larger than the condensate. That we can assume this is really like a vertical, let's say this vertical tube, the diameter of that tube is much larger than the condensation thickness that is building up around that tube, and we can consider that like a flat plate. So this is in terms of the heat transfer coefficients for the laminar region. Now we can find the total heat transfer rate. Just write it a different color. The total heat transfer rate Q is going to be this H average, the surface area available for the condensation times T sat minus TS. And the other thing here is the total condensation rate. And that's the parameter that we often look for. So we want to know for certain conditions, what would be the rate of the vapor that can be condensed for any process that we are looking at. This m dot is going to be Q divided by H prime FG, which would be H of L, AS Tsat minus Ts divided by H prime Fg. So we can get the total condensation rate here too. Now, through the analysis done by Nusselt and the relationship that was found for the delta, we can define the Reynolds number. So the Reynolds number, Reynolds of delta, would be 4G rho L minus rho V times delta 3 divided by 3 mu L square. So this is going to be the definition of Reynolds number, or the relationship for the Reynolds number. Now, if we assuming rho of a density of the liquid is much larger than the density of the vapor that we have, then we get expressions for the average Nusselt number for different flow regimes. So the Nusselt number average for this system, which defines based on HL. This is the average heat transfer coefficient. The characteristic length that we are using is the kinematic viscosity of liquid squared divided by G to the power of 1/3. That's going to have a dimension of length divided by KL. Okay, so if we assume that one and define the Nusselt number like that, then we find for different regimes. Recall that we had 3 regimes here: laminar, wave-free, wavy, laminar, wavy, and then let's call this one turbulent. So laminar, wave-free, laminar, actually wavy, laminar, and then turbulent. So using that one, we can find the Nusselt number for a different regimes. For the laminar, wave-free is going to be 1.47 Reynolds number delta to the power of 1 minus 1 over 3. This is for the Reynolds number delta less than 30. Okay, so this is the, let me just write it down, laminar, wave-free laminar regime. Then for the laminar wavy flow, this Nusselt number, remember for all of them the definition is HL, the characteristic length, times the heat conductivity of liquid. For the other system is going to be Reynolds number delta divided by 1.08 Reynolds number delta to the power of 1.22 minus 5.2. And this regime was happening with Reynolds number delta 1800 greater than 30. And then for the turbulent flow, what you're going to have, this Nusselt number L would be Reynolds number delta divided by 8750 plus 58. Here the Prandtl comes to play. So Prandtl of liquid, power minus 0.5, Reynolds of delta to the power of 0.75 minus 253. So this is for the Reynolds number delta greater than 1800 and Prandtl number liquid greater than 1 or equal to 1. Now we can plot this Nusselt number based on this Reynolds delta. So this Nusselt number L, which is HL times kinematic viscosity of liquid divided by G. Actually, this is square to the power of 1/3 divided by KL. If we make a plot of that, then initially what we have is the laminar at the first 30. Let's say this is 1800, and that's the Reynolds. So what happens here is, let's assume we are dealing with the log scale. So initially it's going to be linear. So we would see such a, probably with the less steep, but it's going to be something like that, and then it's going to go up. Okay, so this is the first regime, this is the second, and this is wave-free laminar. This is wavy laminar, and this is turbulent. So this one is for Prandtl number 1, and if you consider other Prandtl numbers, you would see such a curve. Let's say this is Prandtl number liquid of 10, liquid, Prandtl number liquid of 2, and so on. So we can make a plot of that one for different Reynolds numbers. So we can find out the Nusselt number, and from there we can find out H. Now, if delta is not known, so this is provided that we know delta. Okay, so knowledge of Reynolds number data by the definitions that we had was we would need to know what is delta. So if delta is not known, then we define another parameter called P. Let's define P, and that's KL times L, length of the plate, saturation, minus TS, divided by mu L, H prime FG, the length scale that we have, kinematic viscosity of liquid squared divided by G to the power of 1/3. If we define this P, we can write down again the Nusselt number, the average Nusselt number that we had based on P, 94, P to the power of minus 1/4. This is for the P less than 15.8. So this one doesn't really require the knowledge of delta. So we just need to have the fluid properties, the length of the plate, and that's it, and the pressure. So we get the Nusselt number that we are looking for. And the other one is going to be 1 over P, 0.68 P plus 0.89, 0.82. This is for the P2530, larger than 15.8. And the last one is going to be for L, 1 over P, 0.024, P minus 53. Everything gets times to Prandtl. I will check that one. To the power of half plus 8/9 to the power of 4/3. And this is for the P part greater than 2530 and Prandtl number of liquid greater than 1.